So last time we kind of introduced the concept of asymptotic notation, basically analyzing a given algorithm as it goes towards, as the size of the input goes towards infinity, and we came up with what was known as theta of some given function. And what that basically does is it gives an upper lower bound for whatever running time of your given algorithm we have. And so what we're going to do today is we're going to take a look at this recursive binary search algorithm. And I've kind of written it out in a very simplified form. So this is not actual code here. This is a little bit closer to the side of pseudocode. And we'll break it down in half a second. And so what we have here, right, is a recursive binary search, and we want to perform just a runtime analysis. We want to calculate its runtime recurrence. And what runtime recurrence essentially is we want to figure out, as the size of n approaches infinity, how will it act in the long term. And before we do that, though, let me define a couple of things. Now, we've just gone over what theta of g of n does, right? It gives an upper and lower bound, an upper, right, and lower bound to whatever runtime. Let me write this out in actual words. So upper and lower bounds, right, to your runtime, and lower bound based on whatever g of n is. And the second kind of term or notation that I want to define here is just t of n. And we'll just say t of n kind of represents, for some size n, the worst case scenario for runtime. And this becomes especially important when we have, essentially an if statement. So in looking at this recursive binary search kind of algorithm that we have written out here, actually, when we consider a worst case scenario, what we will be assuming is that we'll be running this if statement to the max. We'll be running this over and over again. And so essentially what this does is it's basically searching for a given value, right? And we're given a key, and we're trying to match that key to some value within your algorithm. Some value within the array of numbers or values, essentially. And so what this binary search algorithm does is it takes your array, right? Just as a quick review, it takes your array and say this is some middle value. This is the very middle of your array, right? And it's going to split in half and say, all right, how does my key compare to this array here? And if your key, and this is a sorted array, right? Just to make things easier, it's a sorted array. And so it says, all right, so if my key is lower than my middle term, what it's going to do is it's going to cut off everything higher than that, because we know it's sorted, it's going from lowest to highest, and we're going to only consider whatever is here. And again, we're going to take again our middle term and compare our key to it, and each time it takes it and it cuts it in half, and that's what this here does. So this is your lower bound, this is your upper bound, this is your lower bound, this is your upper bound. So if your key is less than your middle term, it's only going to take the lower half. If your key is higher than your middle term, it's going to take the upper half, right, from your middle to your high, so your upper half. And so that's fundamentally the concept behind this sort of algorithm that we have here. And so now let's consider and let's perform sort of a runtime analysis on it. So what we have here is a number of ways to do it. So let's zoom in a little bit. And let us begin to consider precisely what we have here. And so the first couple terms are quite straightforward. We can tell this, right? All of these are basically just constant time. So just theta of 1, because, they're only one step. They don't depend on the size of our algorithm, the size of our list that we just put in, because we already know the values of low, we know the value of high, so it's nothing fancy. This down here is where things get interesting. Now, first of all, we compare and we consider this. And so we don't know the actual running time of this algorithm. We definitely don't. And what makes this even more complicated is the concept that it's actually referencing back onto itself. It's telling it, okay, I'm going to run recursive binary search on myself, but just with a reduced, with half of whatever list that we have. And of course, if mid matches the key, we're done. But we're talking about the worst case analysis here because we want to see what's the worst that can happen, right? Remember, T of n represents our worst case scenario. And so what actually happens here is that we have, in this case, because we're considering a worst case scenario, it's referencing itself, but just with an array of half the size. And then we can say, okay, so if that's half the size, then the running time of this is just going to be T of n over 2, because we just took our array and we cut it in half as a part of our binary search. All right, and so with that, we can now say that a recursive binary search running time, right, is going to be equal to, if the size of whatever list is equal to 0, it's just going to be some constant. So we'll just say theta of 1, right? Just to make sure we cover all the ground. But what's more important is what we just discovered right up here, which is that otherwise, if n is not equal to 0, our list actually exists. It has some elements. It's going to be equal to theta of n, theta of 1 plus T of n over 2. Right, and so that's the concept behind your running time. Now we want to figure out, though, what it does in the long run, what it's like as n essentially gets larger and larger, and in doing so, as n gets larger and larger, and we want to consider the worst case scenario runtime for it, runtime T of n, let's go to that. As it gets larger and larger, we're going to have to cut it down more and more times. And so let me clear this space, right? And let's consider, again, this algorithm that we have here, and let's take what we had. So worst case running time, or just our general running time, is basically T of n over 2 plus some constant theta of 1. Now clearly this is a constant, so actually I'll just rewrite it and I'll represent it as a value of c, right, plus some constant. And now if I want to calculate what T of n over 2 is, and we follow this same pattern, actually, then that's just equal to T of n over 2 divided by 2, which is T of n over 4 plus some constant, and again we put on this plus this constant on here plus some constant, and let's go again. So let's calculate what the worst case running time for size an array of size, a list essentially of size n over 4 is, and in this case n over 4 divided by 2 is n over 8. Plus some other constant, plus some other constant, plus some other constant, and let's keep going. So then if we want to calculate what T of n over 8 is, right, that's essentially equal to, again, we just divide the size divided by 2, which is n over 16, plus some constant, plus some constant, plus some constant, and so on, so forth. And actually in the long run, we can represent this as the worst case, and again, remember, we're trying to calculate the worst case scenario here, just because it gives us a better idea in this case of what could happen, is equal to n over 2 to the power of k plus some value, some constant, right? And remember, just a bunch of constants added together equals another constant, which is equal to this. Let me make sure I've got this right. And so in the long run, just for some value k, which k is just the number of times you basically run it, and because n is trying to go towards infinity, right, so is k. Now let's represent this in a certain way. Now what we know additionally is we'll just basically eventually bottom out actually to b, where n over 2 to the k is basically less than 1, right? That's something that we can conclude because it's getting larger and larger, and k is getting larger and larger as well each time we run the loop, which can basically be written as n is less than 2 to the k. And if we take the log base 2 of both sides, then log base 2 of n, which is basically can also be written as log of n, is less than k. And so basically that's what we're aiming for in the long run, right? And so then we can take this and we can basically go back, and then we just a little arrow here, and if we take your general T of n, right, then that should be basically equal to some constant, right, plus essentially some smaller constant, that's lowercase c right there. Maybe c was not the best choice for constant here, multiplied by just the log of n, right, plus this one. And in the long run, this actually just becomes, because, you know, as the number gets larger, you just end up, and just ignore this part here, it just becomes to the point where you can ignore your constants. You can ignore your constants, and you can just write it as theta of log n. And so that's basically just the runtime recurrence analysis, the runtime analysis of this recursive binary search algorithm. It's just a quick walkthrough of it. And so what we want to do, and to tie this back into quantum computing and the foundations of classical computing as well, is just seeing that, all right, so if we calculate each item just one at a time, maybe at best we get a log n sort of version of a runtime. And so it gives us the concept that we need to develop an algorithm that is capable, and log n is actually already pretty good, capable of having a runtime that is as efficient as possible, especially in the worst case scenarios. There are some problems out there actually that exist where the runtime, the very best algorithm runtime that we can get is perhaps, you know, theta of n squared, or theta of n times log n, which is greater than theta of log n. And that becomes an issue. And that's where, you know, especially when you get into things like fuzzy systems theory, where you could have, you know, you have to represent something in multiple states, or not in multiple states, but just as a probability, and have almost a dynamic system. That's where the concept of having a quantum computer that is capable of calculating all these different states and being in these different states at once can make things so much more efficient and so much faster. Alright, that's just to wrap up for today. There's no need to go into deep depth in precisely how to calculate runtime recurrence, but it is useful to be able to illustrate and see mathematically how this plays out in the long run for classical computers. And again, like I said, log n is already a really good kind of version. If you just search for a key and you compare it to every single item on there, you end up with theta of n, runtime theta of n, because you're, you know, for every element you just compare it to the key, and that is, and log n already in the long run is lower than that we can guarantee. And so that's it. That's just the concept of runtime recurrence and algorithm analysis. If you have any questions, just please don't hesitate to visit the qmunitytech website, and don't forget, just stay curious and keep on learning. Thank you.